friends, glad you're still with me. Before we stopped in our previous class, today we shall be handling another subsection, measurement of heat energy by method of mixtures. This is a very interesting subsection as well in thermophysics. But before we proceed, I'd like us to remember what we've always known, that heat flows from a region of higher temperature to a region of lower temperature. Therefore, in this method, we're talking about mixtures, that is between two bodies of different temperatures. When you bring two bodies of different temperatures together, there will always be an exchange of heat. Heat tends to move from the body of higher temperature to the body of lower temperature. So in physics, you can actually use this method to determine maybe your specific capacity, your latent heat of fusion, the latent heat of vaporization, your common temperature, even the initial temperature, and the mass of the two bodies. You can use this method to determine any one of them. I also want to introduce you to an instrument used in this method most times, which we know as a calorimeter. This is actually an instrument used for measuring what? Heat energy. It is used in this method. And what is the role? It enables the transfer of the exchange of heat without heat being lost to the environment. It ensures that this exchange of heat occurs in an isolated environment. That is, no heat is being lost to the environment. This calorimeter most times is lagged with an insulator, most times a cotton wool. This is to enable the heat energy not to be lost to the environment. Again, you have to know that this calorimeter most times is made with either copper or aluminium, because they are wonderful conductors of heat. Having known the basics, I'd like you to know also the principle guiding these mixtures, that's problems involving mixtures, which is also applicable to any problem involving heat transfer. The principle states that the heat lost by the hotter body is equal to the heat gained by the colder body, assuming that no heat is being lost to the environment or to the surrounding. The heat lost by the hotter body is equal to the heat gained by the colder body. Thus, heat lost is equal to heat gained. So this is simply the method we shall be using to solve every problem, every single problem involving heat transfer between two bodies of different temperatures. So let us get into the examples. Alright friends, we have the first example. 0.02 kilogram of dry ice was added to a certain mass of water at 35 degrees Celsius, and the temperature reduces to 25 degrees Celsius after all the ice has melted. Find the mass of the water. And we are given the specific heat capacity of water and the specific latent heat of fusion of ice. For this example, you can see that the water was initially at what? 35 degrees Celsius. And then it was mixed with ice. Remember, it's a dry ice, and then the ice was initially at what? 0 degrees Celsius. That means the ice here is the colder body, while water is what? The hotter body. As I told you, heat will actually flow from the region of higher temperature to the region of lower temperature. That means the water will be losing heat, while the ice will be gaining heat. Do you get me? The water will be losing heat, that is the hotter body. It will be losing heat to the colder body, which is the what? The ice. Remember, we are assuming no heat is lost to the atmosphere or to the surrounding. Therefore, it means that the amount of heat lost by water is equal to the amount of heat gained by ice. I want you to note something, that this ice will first and foremost gain heat to do what? To melt. To melt first. That is specific latent heat. To melt first. To what? Water of 0 degrees Celsius. It will also gain heat to increase its temperature, that's the temperature of the melted ice, from 0 degrees Celsius to what? 25 degrees Celsius. That is the common temperature. The water was at 35 degrees Celsius. It will lose some heat to the ice to also land at what? 25 degrees Celsius. Here, 25 degrees Celsius is the common temperature after the ice has melted. I hope you are with me. So if you have understood this, you can now see that heat lost by water is equal to what? The heat gained by the ice. So if we are okay with this, you can now see that we can simply solve this example to therefore get the mass of the water, which we are actually asked to find. Okay, we have stated the given, the mass of the ice, the initial temperature of the water, the final temperature of the mixture, that's the mixture of the water and the ice, the specific capacity of water, the latent heat of fusion of ice, then the mass of water, which is what we don't know. So to proceed, we first and foremost find heat lost by water. Heat lost by water is mc theta. Here, m is, we don't know it, times 4,200 times, the theta here is the temperature change, which is now initial temperature 35 minus the final temperature 25. Please note, once the body is losing some heat, it should no longer be final temperature minus initial temperature, because it is losing some heat. Therefore, it means that the initial temperature will be higher than the final temperature. That's why I'm now using what? Initial temperature, which was 35, minus the final temperature. So if you proceed, the heat loss is 4,200 times 10. 35 minus 25, which gives us 10. Therefore, we are left with 42,000 M. This is the heat lost by water. We have to now proceed to the heat gained by ice. As I said earlier, the first phase was the heat gained by ice to just melt, and then the heat gained by ice to raise its temperature to 25 degrees Celsius. So the first heat gained by ice is H is equal to mL, which is required for just melting, which is now 0.02 times 3.4 times 10 raised to power 5, which gives us 6,800 joules. This is the first heat gained by ice just for melting. So the heat gained by ice, that's the water which has already melted, to increase its temperature from 0 degrees Celsius to 25 degrees Celsius is H is equal to mc theta, which is equal to 0.02 times the specific heat capacity of water, 4,200 times the temperature change. It is gaining some heat. Therefore, it will now be final temperature minus the initial temperature. 25, which is the final temperature, minus the initial temperature, 0. Therefore, our answer will now be 2,100 joules. So to get the total amount of heat gained by ice, it will now be 6,800 plus 2,100, which gives us 8,900 joules. Then friends, the total amount of heat lost by water is 42,000 joules. Because we are looking for what? The mass. We did not include the mass because the mass was not given to us. It's the unknown we are looking for. The amount of heat gained by ice from melting is 6,800. The amount of heat gained by ice to increase the temperature to the common temperature is 2,100. So the total amount of heat gained by ice is 8,900. So to get our M here, which is the question states, find the amount, the mass of the water. Therefore, it should not be the total heat lost by water is equal to the heat gained by ice. So to get the M, which we are actually interested in, and we've agreed that any method involving mixtures, we have to do what? Use the formula heat loss is equal to heat gained. And we're lucky enough, we found our heat loss by water and the total amount of heat gained by ice. Therefore, the heat loss, which is 42,000 M, is equal to the heat gained by ice, 8,900. Therefore, M, which is the mass of the water, is equal to 8,900 over 42,000, which gives us 0.2. Therefore, the mass of water is 0.2 kilogram. So therefore, you can see that once you are given any exercise involving mixtures between two bodies of different temperatures, you can simply use the formula heat loss is equal to heat gained. Once you've gotten the amount of heat lost, you equate it to the amount of heat gained, and that gives you the answer for anything you're asked to find. You'll be asked to find the common temperature, you'll be asked to find the mass, you'll be asked to find the heat capacity, that is specific capacity, or the latent of fission. Anywhere else you find, you can simply use this method and you are good to go. The second example we have here states is a very simple one. 200 grams of water at 19 degrees Celsius is mixed with 100 grams of water at 30 degrees Celsius. What is the final temperature? Here we're not asked to find much, just the final temperature. Our interest should just be based on the final temperature. We're not giving specific capacity, we're not giving anything. So we assume that what? Heat lost is equal to the heat gained. Remember, the one of the higher temperature loses heat, while the other gains heat. Therefore, it means that the 200 grams of water at 90 degrees Celsius is the one losing heat, while the one at 30 degrees Celsius is the one gaining some heat. Our interest now is to find the final temperature. Heat loss is the mass times specific capacity times, since it is losing some heat, to therefore be the initial temperature minus the final temperature. That is theta 1 minus theta 2 is equal to the mass of the one gaining some heat times specific capacity times, since it's gaining, to be theta 2 minus theta 1. Okay, since we are not given the value of the specific capacity and they appear on both sides, by knowledge of mathematics, we can easily cancel out these two. So we're left with the mass, which is 200 times theta 1, 90 minus theta 2, which is equal to the mass 100 times theta 2 minus theta 1, which is 30. Open up the bracket. 200 times 90 will give us 18,000 minus 200 times this, which is 200 theta 2, that's opening up the bracket, equal to this times this, 100 theta 2, 100 times minus 30 minus 3,000. So you can see that you can easily collect like terms. This is theta 2, so theta 2 coming over here, while this goes over there. This is 100 theta 2 coming over to now be minus 100 theta 2 minus 200 theta 2, which is equal to minus 3,000. This is 18,000 crossing the equality sign, so to change its sign to minus 18,000. Minus 100 theta 2 minus 200 theta 2 give us what? Minus 300 theta 2. Remember our interest is theta 2, which is what? The final temperature is equal to minus 3,000 minus 18,000, which is minus 21,000. So this is theta 2. You divide both sides by the coefficient of theta 2, which is 21 minus 21,000 divided by minus 3,000. The signs cancel out, so you're left with what? 70. Therefore, our theta 2 is what? 70 degrees Celsius. So from this thing we've solved, we can see that if 200 grams of water at 90 degrees Celsius it mixed with 100 grams of water at 30 degrees Celsius, the final temperature will now be what? 70 degrees Celsius. With this knowledge you've gotten today, I think you can boldly go out there, solve more and more questions involving mixture methods, having in mind that heat loss is always equal to heat gain. With this, we've come to the end of a lesson on thermal physics. I'm so glad you've been with me to this very moment. Please stay safe, remain blessed, we are loved. Thank you so much.